This right now, anything I can call back on? Okay, class ends at 9, I'll call you right after that. Okay, glad to. Bye. Okay, you didn't say you're fired, so I guess I'm okay. It'd be fun if I really did say, I told you never to call me here. You didn't know where it was. Let me think. Okay, so what I'm doing with this stuff here is I'm saying, when you had this condition called resonance, you had the inductive and the capacitive impedances equaling each other. All right, so let me erase some stuff so I have room to put it down. So what we're going to find out is that in that equality, x sub L is x sub C, or 2 pi f L equals 1 over 2 pi f C. What we want to solve for is f. Rather than bore you with all the derivations, I'll tell you the answer is going to look like this. F will be equal to 1 over 2 pi f. Hang on a second. Hey. It'll look like that. I have to double check. Okay, I should look at my cheat sheets that I so miraculously put together. Funny, when you don't do something all the time, you tend to forget a few things. Equation for yeah. X sub resonance, come on. I see the one for capacitive inductive reactance, now I'm looking for the one for resonance. They have to equal, and the question is the square root inclusive of the 2 pi f or not? I don't think it is. I think it's, well, I'll look it up and I'll have to get back to you on it. But what you're going to find is, you'll get an equation sort of like that. I don't want to drive it, so I don't want to spend the time doing that and figure out which of the thing.
What's the practical application of that?
All right, the practical application is to say, I want to know what frequency I'm going to get if I pick a particular capacitor and a particular inductor. Exactly where am I going to get that voltage? What frequency am I going to be at when that voltage shows up? And that's how you compute it. What's interesting is, this guy's in the denominator, so if L gets bigger, the frequency of resonance goes down. If the capacitor gets bigger, the frequency of resonance goes down.
Shouldn't that denominator f be missing? Shouldn't it be gone? Because you had f squared. You took the square root of it all. So it's just 2 pi square root of LC.
Okay, so what you're saying, let's say, because I'm solving for f, and I'm going to have f squared when I'm going to have 2 pi squared, what'll be 2 squared, pi squared, f squared, and L and C. So guess what? It would seem to me that if you're solving for f, that what you have to do is move everything to the other side of the equation, which means you have to divide by 2 squared, pi squared, and L and C. Oh, and that'll be f squared. So that's right, when you take the square root of that, this 2 just becomes 2, and the pi just becomes pi, and the LC becomes the square root. So I think I had it right.
No, but the f shouldn't be in the denominator.
You're right. You are absolutely correct. That's right, because we're solving for f.
I'll sleep better now.
2 pi f times LC. Very good. Hey, good catch. Glad to see somebody's awake and paying attention and remembers how to do algebra, because I obviously forget things. what you're trying to do is say, I want to calculate. So as you go up in frequency, the L's get smaller and the C's get smaller. And in fact, a lot of things get smaller. Antennas get smaller. Here's an antenna. Remember, Craig last week talked about a piece of wire, you know, how big would it have to be if it had to resonate at 60 cycles? It's about 3,100 miles, by the way. What he didn't tell you is that whatever that wavelength is, the wavelength is whenever you have a sine wave, the distance, he said something a little bit incorrect. He said cycles per second is when you go positive and negative. Well, it's positive and negative and back to where you started. Whatever you do when you have a cycle, you have to measure from exactly the same point in the cycle. Here's a slope going up, here's a slope going up. This is a slope going down, so it doesn't count. Or you take a peak in the positive end, or you take a peak in the negative end. That distance between these 2 points is lambda. That's the wavelength, the distance from crest to crest of the wave. Why is it a distance? Because the thing is moving at the speed of light. So how far it travels from the time it goes from plus to minus and back to plus again is a distance that it physically goes downstream, that it physically moves. And the rate at which it's doing is the frequency. And they're inverse. When the frequency goes up, the wavelength goes down, and vice versa. And the reason for that is because when you multiply the two together, you get C naught or C, whatever you want to call it, the speed of light. Speed of light doesn't change. Well, it doesn't in a particular medium. In free space, it's called C naught. In copper, it's 95% of that. In water, it's something else. In glass, it's even less. But it's going to be a fixed number in a particular medium. What's the speed of light? Anybody know the numbers?
8 times 10 to the 8 meters per second.
Yeah, some people say 186,000 miles per second, that's their metric, but it's really about 300 million per metric in this world, remember, meters per second. So, if I have a radio that I'm operating in the 2 meter band, I divide the 300, I take this and divide it by the one that I want to find, the opposite of what I want to find. So what frequency is 2 meters? I take the 2 meters here and divide it into the speed of light. And 2 will make that 150 million cycles per second or megahertz. And 2 meters, as we all know, is 144 to 148, pretty close to 150. There you go. The 40 meter band is 7 to 7.3. If you divide 40 into 300 million, you're going to get about 7. So there you have it. Higher frequency, longer wavelength, shorter wavelength, higher frequency, or the opposite. Longer wavelength, lower frequency. Resonance is the frequency when the x of L equals the x of C, and if you do the equation, it comes out looking like that. That's how you calculate it. The important thing to know is not only can you calculate it, you have to learn the simple fact that these both go down in value as the frequency goes up. So if you want to get a higher frequency, either reduce the inductance or reduce the capacitance. Both will give you the same result. And this is the magic of radio. That beautifully, beautiful concept where 2 devices that look absolutely nothing like each other, capacitor and inductor, just they're totally different in appearance and shape and size and everything. And they have absolutely perfectly opposite characteristics. And why is that? This stores energy in a magnetic field. This stores energy in an electric field. And when you have electromagnetic wave, you've got a vector that happens to be an electric one, and you got another vector that becomes the H. And these guys are actually 90 degrees to each other, and they are moving in some particular direction, propagation direction, at the speed of light. By the way, when you look at a piece of wire, the electrons are not moving at the speed of light. Matter cannot move that fast unless it starts there, according to Einstein. well, what's moving at the speed of light? And the answer is the field, the actual field that comes between, looking for capacitor somewhere, the field that comes between the plates that are charged positive and negative generates an electric field, and that's the thing that zips through the conductor at the speed of light, or the speed of light reduced by the medium that you're going through. And you know, if you don't have a medium, if you don't have a conductor, if you're going through free space with a radio wave, that's going to be at the full speed of light. And it's pretty, not only pretty fast. In 1 second, at the speed of light, you go around the Earth about 7.5 times. It takes 140 milliseconds to go around the Earth. So when you're talking to somebody in Australia, you're getting there in about 70 milliseconds. It's pretty quick, less than 1/10 of a second. That's the beauty of it. Although it's enough to be able to make a difference in some things that you have probably observed. For instance, in the days before digital television, remember ghosts on TV? The signal from the broadcast station and your TV set bounced off a tall building, like the Sears Tower, until they moved the antennas there. And in doing so, you got the incident signal, and then microseconds later, you got the one that you had to take the longer route from the transmitter off the building to your antenna. Well, the lines are sweeping across the TV screen. There's 525 lines, and there are 30 full frames every second. 30 times 525 is 15,750. That's how many lines were swept on an old-fashioned analog television set. And if you divide 15,750 into one, every single one of those lines took 62.5 microseconds to sweep. 62.5 microseconds means that if the radio wave had to bounce off of a different building, it might show up a few microseconds late. That's enough for the picture to shift over, the ghost image to be an inch or two from the primary image. That's why you saw it. So you can actually visualize things that happen in millionths of a second if you got the right kind of medium. We've got a right kind of medium device for doing it. It's called an oscilloscope, which has plates that deflect a beam of light from left to right, or from your direction that way. I'm doing stage right. And vertical plates that actually deflect it up and down. Thusly, so here's time, and here's the amplitude. Vertical plates in the oscilloscope are deflecting according to the wave's voltage, and the horizontal is being fed with a sawtooth that goes straight line, and then when it gets to the end, drops down and does a straight line build up again. So it goes left to right, and does it again and again, and that's why you get that stationary wave on the oscilloscope. If you have the right sweep rate and the right synchronization, triggering process, we're covering that too. Oscilloscopes will show you what happens over a period of time. I'm trying to think, was there anything that Greg talked about that I wanted to amplify? There was something that crossed my mind a few seconds ago. Yeah, series and parallel. We'll do that, and then that'll be it for tonight. Next week, I will finally give you something that's going to be what you can put your teeth into. We're going to build a circuit. We're going to actually put some electronics together. We'll build a power supply, which has a transformer that uses inductors. It will have a rectifier, which turns AC into DC, and is nonlinear, and has that feature we call the semiconductor effects. We will have a filter network that uses a little bit of this, a little bit of that, to take all the ripple out of the converted DC that came from AC, and we'll introduce you again to the transistor, which will regulate the voltage so that you get the same voltage whether you draw a lot of current or a little current from it. But real quickly, the series and parallel stuff Greg talked about last week, I just want to go over one more time a little bit differently than he did, just because I think there's a conceptual thing that needs to be put in there that may not have been put in the first time around. What was being explained to you is what happens when you've got more than one resistor in a circuit. Thusly, R1, R2, R3. The total R, the effective R, is the sum. As he said. What he didn't say is why that is. And the answer is because when you happen to have them in series, it's just like you made a bigger resistor out of a bunch of smaller ones. Okay? Same thing with an inductor. If you have inductors in series, it's as if you had one ginormous coil. If you just put them in then. So they add. Same rule there. The total L, or effective L, is the sum. Many as there are. And when you have capacitors, it's not the same. The total capacitance is actually, C1, C2, C3 added up if and only if they're in parallel. And why is that? Because, this is what Greg didn't show that I wanted to get across. It's as if you took the plates and increased the plate area by doing that, okay? That is why parallel capacitances add the same way as series resistances and series inductances do. It's because you're really adding the plate surfaces together when you go in parallel. Now, the other thing I know we covered is if you have them in parallel, there's a reduction, R1, R2, R3, and you saw what the rule was, the R total is the